Okay, so welcome to Math 310, Introduction to Modern Algebra. This is Lecture 7. And what I want to do is I want to do the introduction to the Euclidean algorithm and applications, talk about subgroups, talk about homomorphisms this time, and then go back and talk a little bit about the why do we give a damn? Why are we taking this class? Why is this material useful? What can we do with all of this modern algebra that we're developing? There's a couple of theorems you might remember from calculus. There's the initial theorem, the MVT and the IVT. Does anybody remember what MVT or IVT are? The mean value theorem, yes, and the other one, intermediate. And both of these theorems say, hey, if you have a function that has nice properties, there's a point that has nice properties. What would you love to know? So there's a point that has nice properties. What would you like to know? Where is it? Right? Imagine I'm a political consultant. 2028 is not that far away. And I say, good news. I'm a theoretical mathematician and I can prove your candidate has a path to win the presidency. What is the first question I'm going to be asked? How? Well, it's a theoretical proof. It's an existence proof. I'm not going to be high. Right? It might be useful to know that there's at least a chance, but I would like to know more than there's a chance. I'd like to know how to do it. A lot of times in mathematics, we don't actually need to know where something is. We just need to know that something exists. However, in the real world, when you're doing applications, it's often nice to know where is it. We talked a little bit about factorization last time. Factorization is trivial, right? I give you some number x. Is it a multiple of 2? Is it a multiple of 3? Is it a multiple of 4? Would you ever try, is it a multiple of 4? No, you just, if it's a multiple of 2, try 2 again and keep trying 2 until it no longer works. Doesn't matter. You can factor a number in principle very easily. If you try to do this algorithm on a number of size 10 to the 400, numbers that occur in prime encryption, the universe will die heat death numerous times over before you make any progress. So even though it's trivial to do, it's not trivial to do quickly. So one of the things we're going to do today is we're going to develop a tool which will help us attack a lot of problems in group theory. It'll help us figure out what is the structure of certain groups. Even more than that, it'll allow us to prove that certain sets are groups. For a lot of things, we don't need to know how to do things quickly. We just need to know that something exists. For applications, we need to be able to do things quickly. And so what I want to start off with is one of the greatest algorithms in all of mathematics, the Euclidean algorithm. And so the Euclidean algorithm it is a very efficient way to find integers a and b such that for given integers x and y, we have ax plus by equals the GCD of xy. Has everybody seen GCD, the greatest common divisor? So if I were to say books closed, 10% of your grade right now is going to be you writing down the definition of GCD. Everybody would be happy with that. So can somebody tell me what is the GCD of two numbers? What does GCD stand for? Greatest common divisor. This is the largest integer dividing x and y. Have people seen this before? So if you give me any x and y, the Euclidean algorithm says it turns out to be integers a and b such that ax plus by is the GCD. It turns out these, of course, are not unique. If a and b work, so too does A plus Y and B minus X? Or A plus NY and B minus NX? Because if I increase A by adding NY, I get NYX. If I decrease B by subtracting NX, I get a negative NXY. So I don't change the sum. So there's not a unique A and B, but I can probably make them unique by maybe decreasing their size a little bit. I can keep subtracting multiples of X and Y a little bit. So there's two things going on here. The first is that there are such an A and B, and the second is we can find them quickly. So let's do a proof A and B exist when X and Y are relatively prime. So what does it mean for two numbers to be relatively prime? So if I give you two numbers that are relatively prime, what does it mean? Yes. Excellent. I'm glad that you said one. Right. One is annoying. We've got to keep it everywhere. My freshman math book was talking about vector spaces, and it said sometimes the empty set can be very annoying. So we will tacitly exclude it whenever it causes trouble. But yes, you could consider, but then what do you mean by a vector space where you have no elements? For any vector V in the set, well, there are no V in the set. So how do I want to interpret this? And so let's do the case when X and Y are relatively prime. Okay? So let's consider the set of all things of the form AX plus BY with 0 less than equal to A less than Y minus 1, 0 less than equal to B less than equal to, less than X minus 1. Okay, I'm going to consider this set of objects. How many elements are in this set? So how many elements would be in this set? Well, can you give me an upper bound on how large the set is? How many choices do I have for A? Nope. Why? Because I'm going from 0. How many choices do I have for B? X. So if everything is disjoint, if everything is distinct, I have XY elements. Maybe some of the elements collide. Set is at most X times Y. Okay. So let's see if any of these elements could be the same. Right? I claim they're all distinct mod XY. Okay, so I'm going to say that no two elements, if I choose a pair A1, B1, and I choose another pair A2, B2, they can't be the same mod XY. If not, we have two pairs with A1X plus B1Y equal to A2X plus B2Y mod XY. That's what it would mean for the two pairs to be the same mod XY. So when you look at this, I've got X and Y on the left, I've got X and Y on the right. What would you like to do to something like this? So how would you attack some algebra like this? Go back to what you did in maybe Algebra 1, Algebra 2. I've got x's and y's on one side, I've got x's and y's on the other side.
The x's on one side?
Yeah, put the x's on one side and put the y's on the other. Which should go on the left side? Of course. Never be wrong. Just be wrong. So if we put the x's on the left, we get a1 minus a2x is congruent to b2 minus b1 y mod xy. And that means there exists an m such that a1 minus a2x equals b2 minus b1 y plus some multiple of xy. That's what it means for them to be congruent. What can you tell me about the left-hand side? What's true about the left-hand side? We know it's an integer, but what else do we know is true about the left-hand side? No matter what A1 and A2 are, there's something that's going to be true about the left-hand side. Look at how it's written. We're talking about divisibility. What must be true about the left-hand side? What number must divide the left-hand side? It must be a multiple of x. So this is a multiple of x. mxy is a multiple of x. So what's the only possibility for b2 minus b1 times y? What must be true about that? If the left-hand side is a multiple of x, and half of the right-hand side is a multiple of x, what must be true about the other part of the right-hand side? Also, right? If you want, I could bring all the multiples of x to the left-hand side, and then I would get that this has to be a multiple of x. So this whole thing is a multiple of x. But what did I assume about x and y? They're integers, but I assumed more than just they're integers. What am I assuming about x and y? They're relatively prime. So if x and y are relatively prime, can anything that divides x divide y? So anything that divides x, what does it have to divide? So x, nothing that divides x can divide y, but this has to be a multiple of x. If it's going to be a multiple of x, and x can't divide y at all, I'm sorry? Well, what does x have to divide? It divides b2 minus b1 times y. It has nothing in common with y, no factors in common with y. So what does x have to divide? It does have to divide xy, but we know b2 minus b1 times y is a multiple of x. We know x has no factors in common with y. X can't divide anything in y. Nothing that divides x divides anything in y. But b2 minus b1 times y has to be a multiple of x. Okay, so we know the left-hand side is clearly a multiple of x because it's multiplying by x. We know mxy is a multiple of x because we've got a factor of x. So if x divides this and x divides this, it has to divide their difference. If I take two multiples of x and subtract them, it's still a multiple of x. 7x minus 5x is 2x. 13x minus 3x is 10x. So if I just move this over to the other side, I would have everything on the left as a multiple of x. So this must be a multiple of x. Similarly, I know y divides the factor b2 minus b1y, y divides mxy, so y has to divide a1 minus a2 times x. So everything I'm doing for x, I can do in a moment for y. So we know that b2 minus b1 times y is a multiple of x. And I'm assuming that there's no factors in common between x and y, they're relatively prime. So if 2 divides x, 2 can't divide y, so what does 2 have to divide? b2 minus b1. 3, if 3 divides x, it doesn't divide y, what does it have to divide? b2 minus b1. So what does x have to divide? So x divides b2 minus 1. So x divides b2 minus b1. But look at where b2 and b1 live. They live from 0 to x minus 1. You've got to choose two numbers between 0 and x minus 1, and their difference has to be multiple of x. What's the largest gap you can have between two numbers from 0 to x minus 1? What's the largest gap you could have? I choose two numbers from 0 to x minus 1. How far apart could they be? X minus 1. Choose b1 to be 0, choose b2 to be x minus 1. If I choose them as far apart as possible, is that a multiple of x? What's the only way they could be a multiple of x?
If x is 1.
Nope. Because remember, you don't get to choose x. What's the only way b2 minus b1 could be a multiple of x? So if we took them to be as far apart as possible, that's only going to be x minus 1. That's not enough to be a multiple of x. There's only one way b2 minus b1 can be a multiple of x.
X minus 1 minus 1.
That would be x minus 2.
Plus.
But you can't do plus 1, because b1 and b2 live from 0 to x minus 1. The largest their difference can be is x minus 1. X minus 1 is not a multiple of x. There is a choice of b2 minus b1 that's a multiple of x. What's the only choice? Zero. Right? That's the only way it can be a multiple of x. The only way it can be a multiple of x is if b2 minus b1 is 0, which means b2 equals b1. Thus, b2 equals b1. So the only way I'm going to get a multiple of x is if b2 equals b1. If you're not comfortable with this, please let me know. And we've gone through and we said, let's assume that they're not all distinct. If they're not all distinct, then we get b2 equals b1. Is there anything special about the b's and the y's versus the a's and the x's? So a similar argument gives what? So we just proved b2 equals b1. What do you think a similar argument is going to give about the a's?
A2 equals A1.
A2 equals A1. Right? So you should go through and do that argument, write it out carefully. But we just showed that we can't have two pairs being the same. All the pairs are distinct mod xy. So we have xy pairs, and they're all distinct mod xy. Okay? How many remainders are there mod xy? If you have a clock with 12 hours, how many possibilities do you have for a number mod 12? So on a clock with 12 hours, how many possibilities do you have for clock 12? If you have a clock with 35 hours, how many possibilities do you have? 35. So if we have a clock with xy hours, how many remainders are there? xy. Everything is distinct. So as everything is distinct, must be a choice of A and B such that AX plus BY equals 1 mod XY. So this proves the existence of an A and a B. Okay, and then I could play some games and maybe reduce the size of A and B. If A is greater than Y, I could subtract multiples of Y, it would still be congruent to 1 mod XY. If B is greater than X, I could subtract multiples of X. But this proves I can find A and B such that AX plus BY equals 1. So at first you might be happy, but the problem is, how many A's do we have to look at? 0 is less than equal to A, less than equal to X minus 1, 0 less than equal to B, less than equal to Y minus 1. If X and Y are of size 10 to the 200, then the number of possibilities. So approximately how many pairs of A and B would you have to look at if X and Y are of size 10 to the 200? So if X is of size 10 to the 200, how many A's do we have to look at? 10 to the 200. How many choices of B do we have to look at? 10 to the 200. If you have 10 to the 200 choices for A and 10 to the 200 choices for B, how many choices do you have for the pair AB? 10 to the 400. Good luck. This is a terrific example of an existence proof. We have proved that an A and B exist, and I've given you an algorithm to find them. But you could have to check on the order of 10 to the 400 pairs before you find the one that works. And that's just not practical. Now, how many of you have seen a proof of the fundamental theorem of calculus, that the area under the curve is the antiderivative at B minus the antiderivative at A? Did you actually see a proof where they show that the upper and the lower sums converge to a common value? They often did that by looking at the difference, and they evaluate the difference using the mean value theorem many, many times and taking limits. They don't need to know exactly where the point is. They just need to know that some point exists to make the argument work. Over here, when we want to prove certain things later, our groups, all that matters for a theoretical attack is that A and B exist. So when we're going to prove later, we showed that when we looked at the clock with 12 hours, this was not a group under multiplication. Give me a number on a clock with 12 hours that's not invertible under multiplication. So a clock with 12 hours, a number that's not invertible under multiplication. So somebody give me a number on a clock with 12 hours. 5. Can you find something times 5 equaling 1 on a clock with 12 hours? 5 times 5 is 25. 5 is invertible. Give me another number on the clock. 7. 7 times 7 is 49. Give me another number on the clock. Remember, we talked about, the problem with the number 12 is it was composite. It was looking at the factors that had things in common. So let's see. So yeah, when we're looking at, clock with 12 hours, anything that was a multiple of 2 is not going to be invertible, because no matter what you multiply it by, it's going to be multiple of 2, it's going to be even, it's not going to be congruent to 1 mod 12. Anything that had a factor in common with 12 can't be invertible. And what was amazing is if you take the numbers that are relatively prime to 12, they're all invertible. And they formed a multiplicative group. To prove that, this result that we can find in A and B, that's all we need to prove that it's a group. If we wanted to find the inverses, that would be very different. And when we do encryption, when we do RSA, we need to be able to find these numbers quickly. So I only did the special case when X and Y are relatively prime. So as a good exercise to see if you really understand this, go through the argument and say, what would happen if X and Y shared a common factor D? How would you attack that in that case? So in the general case, maybe write X as, X tilde times D, Y as Y tilde times D, with, GCD X tilde Y tilde equals 1. Maybe try something like that. Okay, so we have enough to know that the A and the B exist, but we don't have enough to prove it efficiently. So now let's go to the Euclidean algorithm. And maybe rather than proving it, well, I'll start proving it in general, and then we might switch to just doing a specific example. So we want to find the GCD of X and Y, and without loss of generality, WLOG, without loss of generality, we can assume X is less than or equal to Y. And so step one is we can write Y as some multiple of X plus a remainder. And where does the remainder live? How large could the remainder be? What's the largest the remainder could be?
X minus 1.
X minus 1. Because if the remainder was X, then we could just increase the multiple of X by 1. So we might as well assume the remainder is at most X minus 1. And now we can write X as some multiple of R1 plus a remainder. How large is that remainder going to be? What's the largest R2 could equal? So I'm dividing X by R1. I get an integer and a remainder. This is just old division from high school. If I divide by 17, what's the largest remainder I can have when I divide by 17? 16. If I divide by 101, what's the largest remainder I can have when I divide by 101? 100. So this is going to be at most 1 minus 1. Lather, rinse, repeat. I can write R2 as sorry. Now I can write R1 as some multiple of R2 plus a remainder. How large could R3 be? So how large can R3 equal? R2 minus 1. And we just keep going. And now we can write R2 as a multiple of R3 plus a remainder. Could this go on forever? Could this never end? Is it possible that I could have infinitely many R's? Or does it have to eventually stop? Is R1 smaller than X? Is R2 smaller than R1? So it's at least 2 less than X. Is R3 less than R2? So it's at least 3 less than X. Is R4 less than R3? Yes, it's at least 4 smaller than X. Could this go on forever? What's the most it could go on? Worst case, X times. So has to terminate in at most X steps. Now, if X and Y of size 10 to the 200, this could be really bad. It could take a long time before it terminates, but it will terminate. And eventually, we will eventually go all the way down, and let's say we have RK equals Q R plus R. And now we got to figure out what the hell the subscripts are. So it goes 2, 3, 4, so they go higher up. So if this is RK, this would be RK plus 1, this would be RK plus 2, and then the Q over here is the same as the K plus 2. And eventually, what's going to happen for RK plus 2? What is that going to equal? 1 or 0. So eventually 1 or 0. If it's 1, you could actually just do one more time, and then you would get a remainder of 0. So if you want to, you could always just keep running the algorithm until you get 0. Okay? So we could keep going, and then we can keep doing one more if necessary, and we will end with a 0. So we would get RK plus 1 is QK plus 3 RK plus 2 plus 0. So we can just keep going if necessary and end with a 0. The reason we're using the letter Q is for quotient. That's what we're getting. We're dividing y by x. That's the quotient. We're using the letter R for the word remainder. So you always want to choose good notation. Okay, why is this useful? So if I had the greatest common divisor of x and y, does everybody agree it divides x? Greatest common divisor divides x. What else does it divide? Y. And it divides any difference of x and y. So what I will do is I will try to copy these. Let D equal the greatest common divisor of x and y. So D divides x and D divides y. Does D divide R1? We know it divides x, we know it divides y. Does it divide R1? How can you write R1? What does R1 equal?
Difference y and 1.
Good. So R1 is y minus Q1x. D divides y. D divides x. So does D divide y minus Q1x? Yes or no? D divides y. It divides x. So does it divide y minus Q1x? Listen. If y is a multiple of d and Q1x is a multiple of d, is the difference a multiple of d? Yes, yes. So d divides R1 as d divides y and d divides x. So we've just shown that if d is the greatest common divisor of x and y, d also divides R1. Imagine d tilde is the greatest common divisor of x, let's do it this way, of R1, comma, and x. Does d tilde divide y? So if d tilde is the greatest common divisor of R1 and x, does it have to divide y? What do you think? How can we write y? What does y equal? Q1x plus R1. We know d tilde divides R1. We know d tilde divides x. So does it divide Q1x plus R1? Yes. So d tilde divides y as d tilde divides x and d tilde divides R1. So this means the greatest common divisor of x and y is the same as the greatest common divisor of R1 and x. So that when I go from x and y to x and R1, I haven't changed the greatest common divisor. And then similarly, lather, rinse, repeat. The greatest common divisor of x and R1 is going to be the same as the greatest common divisor of R1 and R2. And so you get a chain. So the GCD of xy is the GCD of R1x is the GCD of R2 R1 equals dot 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 equals the GCD. It's going to go all the way to the end of RK plus 1, RK plus 2. So we just keep marching down and the GCD doesn't change. And in the last line, it's very easy to find what the GCD is because this is 0. Well, whatever divides RK plus 2 has to divide RK plus 1. And so here, the GCD of RK plus 2 and RK plus 1 is just going to be RK plus 2. And so this is going to just be RK plus 2. So we actually have a way to find the GCD. The problem is this could take a long time. What's the worst thing that could happen now? What's the worst thing for us for R1? In terms of the runtime of this algorithm, what's the worst thing that could happen for us for R1?
Being x minus 1.
Being x minus 1. What's the worst thing that could happen for us for R2?
Being R1 minus 1.
So imagine, how many of you have ever seen Office Space? There's a great line when the guy is going into therapy and he says, every day is the worst day of my life, which means every day is worse than everything he's had up to then. And it's just getting worse and worse and worse. Imagine your life is like that. Every day is worse than the day before. It just keeps getting bad. This would be terrible, right? But it is unfortunately theoretically possible that every single time we only go down by 1. And if that's the case, then the Euclidean algorithm will work, but it will take so long, it won't be useful. So here's a beautiful theorem. Every 2 steps of the Euclidean algorithm decrease the remainder by at least a factor of 2. So for example, okay, so let's imagine we have the following. So we have 0 less than equal to R3 less than equal to R2 minus 1, 0 less than equal to R4 less than equal to R3 minus 1. I claim R4 is less than or equal to 1/2 of R2. that every time I go down 2 steps, I'm going to decrease by at least a factor of 2. Okay? So there's 2 possibilities. Imagine, so case 1, R3 is less equal to 1/2 R2. Then since R4 is less equal to R3, we have R4 is less than equal to 1/2 R2. So this is a great example of case analysis. I want to show that every 2 steps, I decrease by at least a factor of 2. If I decrease by at least a factor of 2 after 1 step, will I decrease by a factor of 2 after 2 steps? Yes. So what I'm saying is, if in the first step, R3 is much smaller than R2, then R4 is also going to be much smaller. So now, case 2, let's assume now that R3 is greater than 1/2 R2. Let's do a calculation. Let's imagine that we have the worst case. So imagine we had the worst case. Imagine we had R1 with some number Q3 R2, and what's the worst possibility for us for R3? What's the smallest change we could have? R2 minus 1. Now we want to write R2 as some multiple of R2 minus 1 plus a remainder. What's the multiple of R2 minus 1 going to be? Is it going to be 1,000? Is it going to be 50? Is it going to be 2? How many times can I take multiples of R2 minus 1 and still be at most R2? 1. So this has to be 1. So we get 1 times R2 minus 1. And what's the remainder going to be? So I want to get R2. I have 1 times R2 minus 1. What's the remainder going to be? 1. So notice what happens. If R3 is really, really large, then that led to R4 being very, very small. So what's nice about this is it can't be too bad for too long. If things are really bad at one level, then you make it up on the next level. Because R3 was so big, it meant R4 was going to become very small. So a lot of times when you're trying to get a sense of how to prove something, do special cases, take some numbers and go through things. So in general now, we're assuming R3 was greater than 1/2 R2. And so we wanted to write now R2 was some multiple of R3 plus some remainder. But we know R3 is at least 1/2 R2. In fact, it's more than 1/2 R2. Could we have a multiple of 2 R3s and still be less than R2? Could I have 2 copies of R3 and be less than R2? No. So since R3 is greater than 1/2 R2, 2 R3 is going to be greater than R2. So we have to have R2 is 1 copy of R3 plus its remainder. So R4 is going to be R2 minus R3, but R3 is greater than 1/2 R2. So if you take R2 and you subtract more than half of it, you can't have more than half of it left, right? If I have 100 and I subtract something larger than 50, whatever's left has to be less than 50. So this is going to be less than 1/2 R2, and that finishes the proof. So every 2 steps, we have to decrease by at least a factor of 2. So for example, if I give you 10 to the 400, how many powers of 2 equal 10 to the 400. Anybody know how we would figure this out? What can we do to both sides? How would you figure out how many powers of 2 do we need to get to 10 to the 400? Well, I think we're doing maybe 10 to the 200. Our numbers were size 200. Anybody know how you would figure this out? Take a logarithm. What base? 10. Doesn't really matter. Sure. So the log base 10 of 10 to the 200 equals, let's call this the log base 10 of 2 to the, can't use x because we use x for other things. Let's use u. So what's the log of 10 to the 200 base 10? 200, right? And that's going to be u times the log base 10 of 2. So u is 200 divided by the log base 10 of 2. Anybody know what the log of 2 base 10 is? I think it's about 0.69. So this is going to be easily less than 400. This is absolutely amazing. If you look at our first proof, we might have to check 10 to the 400 pairs of A and B before we find the one that works. The universe is going to die a heat death many times over. We can't do 10 to the 400 calculations. We then did the Euclidean algorithm, and it worked, but unfortunately, what if it only decreases by 1 every single time? That could still take 10 to the 200. 10 to the 200 is a lot better than 10 to the 400. I'm recording this, so I can't use strong language, but it sounds like fire truck without all the letters. Okay, you're dead. 10 to the 200. That's a square root savings. That's enormous. You're still dead. But now we notice that every time we go 2 iterations, we decrease by at least 50%. All of a sudden now, to get to 10 to the 200, if every time we're doubling where we are, that's less than 400 steps. A computer can do 400 steps without any trouble. This is what makes RSA possible. So again, this is the difference between pure math and applied math. Pure math, hey, we've got a theoretical proof that A and B exist. Applied math, we want to use it. Okay, and if we can't find A and B efficiently, it's useless. The Euclidean algorithm allows us to find them efficiently. Okay, so just very quickly, we talked a little bit about this before, about a subgroup. So if you have a group, you can look at elements that live in the group, and you can collect them. And the question is, which would be good elements to collect together? And so we say a subgroup of G is a subset H where all the elements live in G. And H is a group, if you just consider it amongst itself, with the same group law as G. Okay? So that means if I take and combine 2 things in H, I stay in H. The identity element is in H. I have associativity in H. And if I have something in H, it has an inverse, and the inverse is in H. Some of these things are trivial. Associativity is trivial because G is associative, H lives inside G, it inherits. As long as we assume the identity exists in H, we have the identity. Closure is work. Inverses are work. We know the product of any 2 things in H lives in G, but it may not live in H. And so when this happens, then we have a subgroup. There is a linear algebra equivalent to this. So I think you've all done linear algebra. If you have a vector space, does anybody know the linear algebra equivalent of a subgroup of a group? If I give you a vector space, subspace, right? It's just a subspace. If I give you the 3-dimensional world, a 2-dimensional plane going through the origin would be a subspace. If I gave you a 2-dimensional plane not going through the origin, that might not be a subspace. So there's a lot of similarities, there's a lot of commonalities between things from linear algebra and things in group theory. And so I can give you a group and I can ask you, is there a subgroup? So for example, we looked at 1, 5, 7, 11 under clock multiplication with 12 hours. And that was a group. We showed that that was a group. Can somebody give me a subgroup? There is one trivial subgroup that you should always be able to get. Yes. Excellent, right? The whole thing is always going to work. And then you realize that while you were a smart ass, you could have been an even smarter ass. There's another subgroup that will always work. Can't be empty, because we require something to be in every group. What do we require every group to have? The identity. So modify your completely empty to 1. So these are called the trivial subgroups. You will always have them. So if I ask you, what is a subgroup in your life, depends on it. Say everything or just the identity element, you know you say. Can you give me another subgroup? So you know one element that has to be in it. What element has to be in it? 1. So give me another element to put in with 1. 1, 5. And so it turns out 1, 5 is a subgroup. Every element has its inverse in here. 5 times 5 is 1. 1 times 5, it's closed. This works. What about 1, 7? Yes. What about 1, 11? Yes. What about 1, 5, 7? Is that a subgroup? Does every element have an inverse in this set? Yes. I have the identity, I have associativity. What's the last thing I need to check? Closure. What's 1 times 5? Sorry, 35. And what's 35 on a clock with 12 hours? 11. So not a subgroup, as 5 times 7 is 11. So not every set of elements is going to be a subgroup, but a lot of sets of elements will be subgroups. Okay. So the really hard things are to check to see which things work. Okay. So let's look at the clock with n hours, and let's study the elements relatively prime to n. Okay. And so I'm going to just use some notation. So does everybody know what z like this stands for? What is this?
Integers.
Is the integers. What is n times z going to be? These are going to be the multiples of n. Integer multiples of n. So it's actually dot, 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 minus 2n, minus n, 0n, 2n, dot, dot, dot. And then here's the new notation. Z mod nz is going to be defined to be the integers, 0, 1, 2, dot, 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 n minus 1 under clock rules. So we'll talk later as to why this is good notation. But we're basically saying we're going to consider two elements the same if they differ by a multiple event. And that's what the slash and z is basically saying. It's like we're dividing out by multiples event. We're saying two things are equivalent if they differ by multiple event. And then the next one is z mod nz star. This is it's all m in z mod nz with the GCD of m and n equals 1. So for example, if n equals 12, what are the numbers relatively prime to 12? We've done this several times, including about 2 minutes ago. So what are the four numbers relatively prime to 12? Nope. It's okay. You can call me professor. You don't have to. So try again. What are the numbers relatively prime to 12?
1, 5, 7, 11.
5, 7, and 11. If I give you n equals 7, what are the numbers relatively prime to 7? 1. What's next? There's 2 relatively prime to 7. 3, 4, 5, 6. In fact, if n equals p is prime, right, what are the numbers relatively prime to p? It's just everything, 1, 2, all the way up to p minus 1. So we saw a long time ago, maybe I can scroll and find it. Yes. When we looked at the multiples, we said two numbers are the same if they differ by a multiple of 12. Can I get a group from this under multiplication? Well, I know if I have 0, I'm screwed, because 0 is not going to have a multiplicative inverse. So what if I just look at all the numbers that are not 0? If I look at 1 to 11, does that give me a group under multiplication? And we started doing the table and we just saw we were screwed in so many places. So they said, all right, well, let's just restrict to numbers that are relatively prime to 12. And now we only had 1, 5, 7, and 11. And we saw when we made the group table, hey, this is actually a group. It's a little bit strange. We now have 4 solutions to the equation x squared is the identity. But it's a group. So we have one data point. So given the one data point we have, do you think if instead of using 12, if I used maybe 30 or 90 and looked at all the numbers relatively prime to 30 or 90, that would form a group? Are you willing to conjecture yes based on one data point? No. Like, what should you do?
Get more.
Get more. All right, so give me a number. That's composite.
6.
Okay, it works. Everything's invertible. And it's closed. Give me another one.
8.
Yes, it works. I'll do one more.
14.
Yes, it works. Now what are you willing to do? Will you make the conjecture? Or maybe you gave me numbers that had a special extra property. This occasionally happens in cryptography, is people don't realize that they were not choosing things completely randomly, and people have cracked things because of that. So what we're going to do now is let's look at all the numbers relatively prime to n, and let's see if this is a group under multiplication, okay? So let's study z mod nz star. This is all integers from 1 to n minus 1 that are relatively prime to n under clock multiplication. So the question is this a group? How many things do we have to check? How many things do we have to check? 4. What's the easiest thing to check? Easiest thing to check. Associativity. It's inherited, so it's true. It's true when we just looked at numbers mod n, it's still going to be true here. What's the other thing that's easy to check? What's the other thing that's easy? Identity. Yes, as the GCD of 1 and n equals 1. So 1 is in Z mod and Z star. Now we have the tougher ones. We have closure and we have inverses. So closure. Assume X and Y are in our set Z mod and Z star. So the GCD of X and N equals the GCD of Y and N, and both of those equal 1. Right? X and Y have no factors in common. Then what's true about the GCD of X times Y and N? If X has nothing in common with N and Y has no factors in common with N, what's true about X times Y? So X has no factors in N, Y has no factors in N. Could there be a factor in common with X, Y, and N? So imagine 5 divides N. 5 doesn't divide X, 5 doesn't divide Y, but 5 divides X times Y. Can that happen? So this is where we use if a prime divides a product, it has to divide one or the other. So there's no way I could have a prime dividing X times Y without it dividing either X or Y. So if not, have a prime P dividing X, Y, and N. And if P divides X, Y, then P divides X or P divides Y, contradicting the relative primality. Okay. So what's the only thing that's left? What do we have to show? Inverse. Right. So inverses must show if X is in Z mod and Z star, then X has an inverse under multiplication mod n. Okay. So we need to find an element x inverse such that x inverse times x is congruent to 1 mod n. I think I might have mentioned this before, the principle of Chekhov's gun. How many of you know the principle of Chekhov's gun?
Yes.
Yeah, if you, this, I think, specific as to exactly how long you can wait before you fire it. But, typically, you only have so much space. If you introduce something, it's got to be used. What did we start today doing? What was I really excited about showing you guys? Euclidean algorithm. Anybody want to guess what might be useful here?
Yeah.
I was wondering if you were going to say Euclidean algorithm or Chekhov's gun, but yes, the Euclidean algorithm, right? So let's use the Euclidean algorithm. So let's use the Euclidean algorithm. We need two numbers to use the Euclidean algorithm. Anybody want to tell me what two numbers we should use? There are only two numbers that I've mentioned right now for inverses. What are the two numbers? What should those two numbers be? But we don't know x inverse. N. That's all that we have. So again, I'm trying to emphasize how you do proofs. What do we have? We have x and n. That's it. So we need to somehow use them. So thus, there exists A and B such that A times x plus B times n equals the GCD of x and n. But what's the GCD of x and n? Because x is in the set of elements relatively prime to n, what's the GCD of x and n? So what's the GCD? 1. So ax plus bn equals 1. Or what does ax equal? Let's solve for ax. What does ax equal? 1 minus bn. Or ax is equivalent to 1 mod n. The Euclidean algorithm tells us that we have an inverse. It's wonderful. Not only does it tell us that we have an inverse, it actually gives us a way to find it quickly. However, at this point, I'm just asking, is this a group? Do I need to be able to find it efficiently to prove that it's a group? I just need the existence. So if I only need the existence, could I do this crappy proof from the beginning of the lecture? Yeah. That proof is sufficient to show that there are some A and B such that ax plus by equals 1. So this crappy proof, if all I care, was there a question or? Okay, so if all I care about is proving that there's an inverse, this was enough. If I want to do RSA, this is not enough. Okay. So we just showed now that we can invert. So we now have that these are groups. So when we did the numbers that were relatively prime to 12, that was a group. If I look at the numbers relatively prime to 210, do I have to do the multiplication table? No, I know it's going to work out. And this is why, when I was going like this, I wasn't doing any calculations in my head. I knew it would work out. Okay. And so now, just skipping a little bit ahead, to just do some of the other stuff from the chapters, let G and G prime be two groups. So a homomorphism from one group G to another group G prime is a function phi satisfying phi of the composition of G1 and G2 is phi of G1 composed with phi of G2. So what you should look at is I have some group here, G, with elements G1 and G2. And I have another group over here, G prime. And what I can do is I can take my elements G1 and G2 and I map them. Maybe G2 goes here, maybe G1 goes here under this map phi. We've all seen this before, maps from one set to another. A map from one set to another, that's not really exciting. What's exciting is it says the map is very respectful to the two group multiplications. So in the book, Silverman remarks, these are not really the same dots. This dot is multiplication on G, and this dot is multiplication on G prime. We really could use different notation. If you wanted to, I could be really pedantic, and I could say phi of G1 dot with a subscript capital G to say it's multiplication on the group G, G2 equals phi of G1 dot with a subscript G prime to say it's multiplication with respect to the group G prime, phi of G2. Nobody wants to read that. And so what we say is, look, we're going to just assume that you guys understand what's going on. We're not going to put all the subscripts. We're just going to use the dot for the multiplication on the group. Just know where things live. And what this is basically saying is, I can combine G1 and G2 and then apply phi, or I can apply phi and then combine. Does order matter? Order does not matter here. Order does not matter. What is the square root of 9 plus 16? It is plus or minus 5. What's the square root of 9 plus the square root of 16? Square root of 9 plus square root of 16. Square root of 9 is 3. Square root of 16?
Plus or minus.
4. So we're doing the positive, we'll do the positive square roots. So 3 plus 4 is 7. They're not equal. The square root of a sum is not the sum of the square roots. In general, you can't just mix things around, right? You can't combine and then apply your function. That's not the same as applying your function and then combining, right? So a group homomorphism is very special. It says, I have a mapping between two groups, and I can first combine and then apply phi, or I can apply phi and then combine, and I'm going to get the same answer. So one of the ideas, one of the goals is to try to reduce complicated objects to simpler objects. Sometimes you have more than one representation of the same thing. And this is going to allow us to say, actually, two very different things turn out to be the same. We saw this in some of the proofs by story. We proved the Pascal identity by telling a story. I think we were using Ivy League schools, I think Princeton and Yale. And so sometimes if you look at things one way, it's easier than if you look at it another way. And so then here's a nice proposition. Let E and G be the identity element of G, then phi of E is the identity element of G prime. So it moves the identity to the identity. Let G be an element of G, then phi of G inverse is the inverse of phi of G. And so let's try to prove these. So, we have for all G1, G2 in G, that phi of G1 dotted with G2 is phi of G1 dotted with phi of G2. Let's prove A. So this is all we know. We know G and G prime are groups. We know phi is a map between them. And we know whatever we choose for G1 and G2, we have to have this relation. What should we choose for G1 and G2 for part A? We can choose anything we want. What do you think would be a good choice? Any thoughts? What could we try for G1 and G2? We want to try to show that phi of E is the identity of G prime. What should you take for G1 and G2? Any thoughts? What elements do we know that G has? What else do we know that G has? Do we know anything else? Do we know any other elements other than E? All right, we're gonna play a game. Toss a coin, heads I win, tails you lose. It's possible maybe it lands on its side, but do you like this game? How many choices are there as to who's gonna win? One. Heads I win, tails you lose. If I don't tell you anything about G, what's the only element we know G has? What's the only element we know G has? E. What should we take for G1? What should we take for G2? Let's see what happens. Thus, phi of E dot E equals phi of E dot phi of E. Well, on the left-hand side, what's E times E? What does E times E equal? E. So this implies that phi of E equals phi of E dotted with phi of E. But we know G prime is a group. Phi of E is in the group G prime. What could I multiply both sides by? So I'm trying to show that phi of E is the identity. Right? What could I multiply both sides to cancel this? Yes. Okay, but I can't say 1 over. So instead of saying 1 over, say the inverse. So I multiply both sides by the inverse. So phi of E inverse times phi of E equals phi of E inverse phi of E phi of E. And now we use associativity. What is phi of E inverse times phi of E? What does that equal? I take phi of E, I multiply it by its inverse. What am I going to get? The identity. But now you have to be more specific. Which identity? There are two identities in play. There's the identity in G and the identity in G prime. Is this the identity in G or the identity in G prime? G prime. So this is going to be E prime. And now I'm going to get E prime, if I group these two together, times phi of E. Therefore, E prime is just phi of E, because whenever you multiply anything by the identity, you get back yourself. So this proves that the identity is sent to the identity. The next one is we want to show phi of G inverse I think was the inverse of phi of g. Yes. Is the inverse of phi of g. So if I give you phi of g inverse times phi of g, let's just compute this. What is phi of g inverse times phi of g?
G inverse times G.
Yeah, phi of g inverse times g. What is g inverse times g? So g inverse times g is? No, just g inverse times g.
Oh, E.
E. It's the identity. Which identity? The identity of the group G. And we just showed what the identity goes to. What does the identity go to? It goes to the other identity, E prime. Thus, phi of G inverse is the inverse of phi of G. Yes or no? Did we finish the proof? No. What do we have to do?
P of G times P of G.
Yeah, we have to do the other way. And this is why you really want to prove the lemma that if you have a left inverse, the left inverse is also the right inverse. Because otherwise we have to do that one little extra step. But what I hope you see is there's a natural order to proving these things. So we did a lot today. We gave the proof that if you look at the numbers relatively prime to n, it forms a group. This is one of the most important groups in cryptography. We showed that we just need the existence of A and B such that AX plus BY is the GCD of XY, but we can do it efficiently. And when we try to do cryptography later in the semester, that's going to help us do things in a quick way. All right, so I'm going to close the class now.